All right, I want you to look at some of the data on your wave sheet from yesterday. Over here where we had the radio waves, which were really weak, we want to make sure that up on the top you write down that the wavelength is approximately 10 to the 12th meters. That's big. Those are huge waves that can cover the planet. That's why the ham radio waves went around the world. In the middle here, our waves had shrunk down to about 10 to the negative 6th meters, which is micrometers. That is smaller than a millimeter, 1,000 times smaller than a millimeter. So that's very small. And then on the far end over here, that was in the visible light in the middle, and then on the far right side where we have cosmic radiation, you can understand why this is able to go through a building, because 10 times 10 to the negative 12th meters means that we are taking 1,000,000 times smaller than a millimeter. Okay? So the other thing I want you to see is, as we go across here, talking about all these waves, the frequency, because it's getting smaller, increases. Everybody sees that, right? So as the frequency increases as we go across, so does the energy. On the top of the sheet I just handed you, we're going to learn how to calculate the energy in wave transfer. So in any wave that is in the electromagnetic spectrum, we are going to learn exactly how much energy is in any one of these waves, because we have two formulas here that'll allow us to calculate it. The first formula here, E equals hv, is known as Planck's equation. Max Planck, a scientist, created this equation to find out the energy involved in a wave. So the formula is simply E, which stands for energy, which all right, continuing where we left off. E stands for energy, which is measured in joules. H stands for Planck's constant, which is a number that will not vary. The V there is a Latin symbol for frequency, which is measured in hertz. Down on the bottom, that's Planck's equation. The equation below from Albert Einstein, some of the other scientists, is the speed of light equation, which stands for C, which is the speed of light, which is measured in meters per second. We have wavelength, which is measured in meters because length's metric unit is meters, and frequency, again, is in hertz. The one thing I want you to notice is both equations have frequency, which means if we solve for one equation, we will be able to use that to solve for the other. So these two equations are very closely related to each other. We're going to work together to solve problem number one. Number one has two parts. I want you to take a second here. I want you to read through this statement, and then I want you to look at the two equations that we just wrote down, and I want you to tell me which one of the two would we need. Is this equation going to be E equals H times V, or C equals lambda times V? Take a second, talk with your partner. The equation you should have selected was E equals H times V, because the equation is asking for the energy and giving the frequency. So I'm going to substitute in. I know I will not know the energy, but I know that H is right up here. It is right there. So if you can circle your information, H is 6.63 times 10 to the negative 34th. Now we find V from the problem, and V is going to be times 2.68 times 10 to the 14th hertz. I'm going to add that I don't want to make this too simple, but A equals B times C is just the same problem as what you have right here. If B was 3 and C was 2 and you came up with 6, that's pretty easy, right? Well, if H is 6.63 times 10 to the negative 34th, and V is 2.68 times 10 to the 14th. It's just as easy as long as you got a calculator that you can put it in. So go ahead and punch those numbers in. All right, so to finish, when I punch all this into my calculator, I get 1.77 times 10 to the negative 19th. Now, good question someone asked earlier here. Why do I go to three numbers? Well, I got three numbers in this problem and three numbers in that problem. So I'm going to round my answer to 1.77. It actually rounds up, to 1.78 times 10 to the negative 19th. It's energy. That is in joules. Now, let's go to the next part where it says find the wavelength. Okay, well, wavelength is in the other equation, which was C equals lambda V. Well, what do we know in this problem? We know C, the speed of light, up here, speed of light. So I'm going to put in 3.0 times 10 to the 8th equals wavelength, we don't know, times frequency, we do know, 2.68 times 10 to the 14th. Now, for the algebra people in here, all we've got to do is divide both sides by the 2.68 times 10 to the 14th. So those cancel. So I bring that over here and I take that 2.68 times 10 to the 14th. So 3.0. Hit your exponent in there to the 8th. Divided by 2.68. Get your exponent in there to the 14th. And I come up with 1.1 times 10 to the negative 6th. This is wavelength, so it's meters. Now, if we go back and look, you will see that that is very, very near the visible light spectrum. So maybe this is a ray that is purple or blue. I want you to give number 2 a try and then make sure you answer the questions on the bottom and the back side. This will be due by Friday so that you can ask questions on it while we're putting your portfolios together. This is item number 12. Work with your table partners. You can work in groups, but try and answer 2 on here together with your group. And if you if you get done, go ahead and go on to the back and work on the next ones. I will be here tomorrow before school so you can ask questions. I'll be here after school, or I will not be here after school tomorrow. I'll be here before school this week, but they're not due till Friday, and we will talk in class.